to episode 7 of Ultra Frontier Explorer here on AlwaysAroundNet. In this episode we'll be looking at space weather, and we'll find out how extreme solar storms could wreck electrical technology all across the globe. We'll also learn about the latest scientific research which suggests that it may be harder than scientists previously thought to predict whether or not any one particular solar storm will actually strike the Earth. Now, you're probably asking, what exactly is a solar storm? And that is a very good question.
Solar storm is an informal name for a sequence of very energetic events which are thought to spring from magnetic reconnection of huge and incredibly powerful magnetic fields on the sun's surface. These magnetic reconnection events often happen in or around sunspots where the sun's magnetic field is highly concentrated. Magnetic reconnection events involve enormous amounts of explosive energy, up to the equivalent of 1 billion megatons of TNT. To give you an idea of how huge that is, that's over 300 million times the total of all the explosives used in World War II, including both atom bombs. Energy from magnetic reconnection pours into a solar flare, which emits both a massive pulse of broad spectrum radiation, all the way from radio to gamma waves, and also blasts a gust of solar energetic particles out from the sun, travelling at a significant fraction of light speed. Solar flares that happen to be pointed at Earth can disrupt radio communications when the UV and X-rays hit Earth's high atmosphere about 8 minutes after the solar flare first goes off. Radio disruption is also an effect that the fast-moving solar energetic particles can have if they happen to hit Earth several hours afterwards, where their collisions with air in the high atmosphere creates auroras. The solar energetic particles can also endanger astronauts and spacecraft, especially if they are in high orbits outside the protection of Earth's magnetic field. There's sometimes a third component in a solar storm, which is the most dangerous of all to us Earthlings. Sometimes magnetic reconnection pinches off a loop of magnetic field, blasting off a big chunk of the sun's superhot plasma from its surface. This is called a coronal mass ejection, abbreviated to CME. The first coronal mass ejection observed by humankind was the Carrington Event in 1859, when a huge, fast-moving CME struck Earth just 17 hours after a solar flare, distorting Earth's magnetic field and creating a massive magnetic storm across the globe. The resulting auroras filled the sky in spectacular fashion, with the aurora borealis being visible as far south as the Caribbean. And the auroras were so bright in the northern USA that some people mistook them for the dawn light and began preparing their breakfast. More ominously, the huge magnetic disturbance induced strong electrical surges and sparks in the telegraph systems that spanned Europe and North America, disrupting most instant long-distance communications at the time. It's these induced electrical currents created by coronal mass ejections hitting Earth that makes them such a great threat to our highly electrified civilization today. In 1989, a smaller magnetic storm knocked out power across most of Quebec, but as inconvenient as that was, it's small potatoes compared to the damage another Carrington-class coronal mass ejection could do to us. In the summer of 2012, there actually was another giant Carrington-class solar superstorm. Luckily, when the huge coronal mass ejection blasted across the path of Earth's orbit, our planet was out of the way a few days further along. If that coronal mass ejection had struck Earth, the magnetic storm and induced electrical surges would have destroyed vital power transmission grids and transformers and would have wrecked electrical and electronic equipment across the world, doing an estimated $2 trillion worth of damage and knocking civilization back decades. What's more, one physicist estimated there's a 12% chance of another huge Carrington-class coronal mass ejection like this hitting the Earth in the next 10 years. Here we can see footage of the massive 2012 CME from a variety of viewpoints as captured by various solar monitoring spacecraft. The CME actually hit NASA's Stereo A spacecraft, but because Stereo A orbits the Sun far away from Earth's magnetic field, it didn't experience the induced electrical currents we get on Earth, so luckily it survived to provide us with loads of useful data. One of the key discoveries was that the giant 2012 coronal mass ejection was moving so fast because it had been preceded by another CME that erupted from the Sun 4 days earlier, ploughing a path through the spiral magnetic fields of the interplanetary solar wind, which would otherwise normally have had a braking effect on it. It's thought the same previous path ploughing had happened shortly before the 1859 Carrington Event too, which is why Earth was hit by the 1859 CME just 17 hours after the solar flare was seen, much faster than the usual 1 to 5 days it should normally take for a CME to reach us. What's more, the 2012 coronal mass ejection was actually a double whammy of 2 CMEs travelling 10 to 15 minutes apart. New work from researchers at Reading University here in the UK may help explain why such 1-2 punch CMEs occur. According to Professor Owens, up until now it has been assumed CMEs move like bubbles through space, responding to forces as though they are single objects. However, they're actually more like an expanding dust cloud or a giant sneeze made up of individual plasma parcels all doing their own thing. This makes trying to predict the shape and movement of coronal mass ejections as they plough through the solar wind extremely difficult. Perhaps if the solar wind varies strongly enough, it's possible that it could tear one CME cloud apart into 2. Clearly, we need a much more thorough understanding of the solar wind. Now, something we definitely do know about the solar wind is that when the Sun moves into the quieter, less active half of its 11-year cycle, then the interplanetary solar wind gets thinner and weaker, so it has less of a braking effect on any fast-moving coronal mass ejections. Which means if the Sun does sneeze out a huge CME in the direction of Earth, it would hit us faster and harder, inducing stronger magnetic storms and wreaking greater destruction on our electrical technology. Now, we're currently in solar cycle 24, dropping into the minimum period of solar activity. The thing is that most of cycle 24 has been unusually low in activity. In fact, it's shown the lowest activity since accurate records began around the year 1750. Scientists at the University of Reading predict that by around 2050, the Sun's overall activity will drop to the kind of grand minimum that we've not seen since the 70-year-long Maunder minimum, which was way back in the 17th century. That would mean a thinner, weaker solar wind lasting for decades. You're probably wondering if there's any good news in all of this. Well, yes, there is some. Right now, humanity has the best early warning systems monitoring the Sun in history. There's a whole fleet of spacecraft dedicated to solar monitoring, with no less than 4 in orbit directly between Earth and the Sun, providing data on any incoming solar space weather before it hits Earth. Indeed, yielding enough data that US federal agencies can provide real-time online space weather forecasts to the public. Also, some governments and corporations are waking up to the danger of solar storms and are starting to take some action to reduce the predicted disruption of electrical infrastructure. Although there's still a lot of work to be done before humanity is really ready to ride out another Carrington Event without it suddenly throwing us back about 100 years, technologically speaking.